So this is Unit 1, Transformations, and the topic is absolute value transformations of a function. So absolute value can be applied to a function in two ways. It can change the y values or it can change the x values. For this first one we're looking at, it's on the outside of f of x, and we all know that f of x is equal to y, so it's similar, or it's exactly the same as applying the absolute value to y. Therefore, we are changing the outputs. We are making them all positive. So with this one, this means we have no negative y values. No negative y values. So we saw similar examples of this. If we have a quadratic and it's facing up, and then we apply the absolute value to it, it is going to change these y values down here. They are going to be reflected and then end up above the x-axis, but have the same distance that they had below it, just now above it. So when we transform this using that absolute value, the tails are going to stay up, but now the vertex is going to be above instead of below. Now with this one, this means that there are no negative x values. No negative x values. So the positive domain outputs reflect over the y-axis. What does that mean? So let's take, let's try, what's a good example for this one? Let's try x cubed. We'll try x cubed. So we have x cubed, all right? And we want to apply the absolute value to the x, to the inputs, to the x values. So let's take a look at this. So if I say I have f of the absolute value of -1, I am applying the absolute value to the input, which means now instead of -1, I am going to use f of 1. I want the output that is occurring at x equals 1, which is going to be, we'll use a different color, it's going to be here. And for x cubed, for that particular function, it's y is equal to 1. This means now that this is going to be equal to 1. So now technically f of -1 is going to have an output of +1. So this becomes reflected and it is now over here. That's what it looks like. But it's not a direct reflection, all right? Because we're not using x equals -1. It doesn't exist anymore. What's happening here is that we are literally, I don't know how to, let's do partial. We are literally erasing anything that is on the left side of the y-axis, and we are stealing the outputs from the positive values. Because anytime that we put a negative value in here, it's going to become the positive x value, which means we are now using the outputs all from the positive side. Okay, so whenever the absolute value is applied to the inputs, all the negative x values go away. They literally vanish because they no longer exist. So therefore, we steal the output values from the positive side because now all of our negative x values are positive. And that should not look like a quadratic. That's just a coincidence, not from x cubed. Okay. Let's see. So example 7, use the graph of f of x to graph transformations below. Okay. So with this one, we have the absolute value of f of x plus 2. There's two transformations occurring. We have a horizontal translation, and we have an absolute value. So I'm going to go ahead and use a transformation table. You don't have to, but it does help. And again, we are going to ask you to do a transformation table, so the practice is going to be good. So we already see 3 key points that I want to use. This one, and this one. But the absolute values are on the outside. So we are changing the y values. We are flipping the negative outputs, and they are now going to be positive outputs. This reflection is occurring at the x-axis. So in order to help graph this correctly, I also want to include my x-intercepts. So in total, I'm going to have 5 key points that I want to use. Again, because we are changing the y values, we want to include the x-intercepts. So our x values, we're going to have -3. The first x-intercept, that is -1, 0, and then at -3, -4. The next point is 1, 4. The next x-intercept is 3, 0, and then the last point is going to be 4, -2. All right, so the x values. The only transformation we have is the horizontal translation, and it has a value of -2. So we'll do x minus 2. So we'll subtract 2 from all of the x values because it's shifting to the left. So -3 minus 2 is -5. -2 minus 1 is -3. We get -1, +1, and then +2. For the y values, we are just taking the absolute value. All of them will be positive. So that changes -4 to 4. 0 stays the same. 4 stays the same, 0, and then this -2 becomes +2. Whenever we ask you to sketch on an assessment, you will always have the graph provided. But in the notes, it's just not there because I apologize, but it's something I overlooked. But just get used to graphing them. So we have our x-axis and our y-axis. And I need to look at the transformed values. So my x values, I'm going from -5 to 2, it looks like. So I should have included more of the negative. Oh, I guess I still can. There we go. So we'll have 1, 2, 3, 4, 5, and then 1, 2. And then vertically, we are going from -3 to 4. So 1, 2, 3, 4. And I think I still have the partial on. Yeah. So I can add a little bit more down here. And then 1, 2, 3. Okay, so graphing this, the first point is -5, +4, which is going to be over here. -3, 0, that's our x-intercept. Go ahead and connect those. -1, 4. We have 1, 0, and then 2, 2. And there we go. So now if we look at this, all we did was flip up the tail. It went up this way. We also flipped up this tail, and it went this way. But it helped to have the x-intercepts in there so that we can connect the line segments correctly. All right, part B, we are now applying the transformation to the inputs. Okay, so we're using the same graph. So what I'm going to do is I'm going to steal this graph, and I'm only going to graph the right side. The left side literally vanishes. It's gone because all of the negative input values have disappeared. So we are going to steal the output values from the positive x values. So get the axis. And then I have the points. I'm just going to steal the points from here. I can use those. Okay. So we have 1, 2, 3. And then I need to go a little bit lower. And then 1, 2, 3, 4. And then vertically, 1, 2, 3, 4. And then the positive direction, 1, 2, 3, 4. Okay, scaling's a little off, but we'll see the points still. All right, so we have, well, I guess I'm going to ignore the negatives. They're gone. Gone forever. So we have 1, +4. And then 3, 0, and then 4, -2. Now, just like when we were applying it to the outputs, it's reflected over the x-axis, so we wanted those x-intercepts. You also need to include the y-intercept for this one, and it's at 2. Ooh, I kind of messed that up on mine. Oh, no, we had that shift over, so it changed there. We'll see. All right, so I have my y-intercept at 2. And then from here, that's when the values are going to start reflecting. So at -1, the value is +4, which implies that at, nope, that should be +1. So I'm talking about this point. So this is 1, 4. Therefore, we want -1, +4. So we're stealing the output from the positive 1. And then over here, we have an x-intercept at 3. Therefore, we'll have an x-intercept at negative 3. And then over here, this point was, I believe it was 4, negative 2. Therefore, at negative 4, we'll have negative 2 as well. So all of that is reflected. All right. Hope this helps. Thanks.